have to say that I'm thrilled too, because really we already have more data than we can handle, and when we launch Hubble's successor, which is what the Webb Telescope is, we need to make sure that what we do with it is really the cutting edge science. So really find the things that no one's been able to find before and go and look at them with Webb so that we learn more about the universe. Now, Libby, who's going to be talking later, is one of my science team. I have about 70 scientists in my science team, and believe me, that's not enough. So the way astronomy works now is it is through big teamwork, because there's so much data and there's so much to understand. So the team is sort of organized with scientists leading different areas of science, and then they will put together a team to look at that area of science, because Webb can do many, many different things. And Libby is a real expert in dust. I'm not. I'm interested in dust, but it's not really my field of expertise. So if she's in my team, you're going to be in her team. But I'm going to start by telling you a bit about why the Webb Telescope is so incredibly exciting. And it really is because it's going to be the biggest space telescope ever built. And it is so big that it does not fit in a rocket. So it has to be folded up to fit in the rocket. And that makes it technically very challenging. So for the last 20 years, believe it or not, I have been leading the team that's been building just one small part of this. I have in no way, really built something big or huge. The thing I built is about that big. It's about 1 meter on a side. The telescope primary mirror is 6.5 meters in diameter. So this big gold shiny mirror is 6.5 meters in diameter. And it's cooled by a sunshade. So what we want to have happen, because we want to look at infrared light, which is heat radiation. If you think about it, you wouldn't go trying to look at some faint little light while shining a great big lamp on it. So if your telescope is warm, it's like your telescope being a great big lamp. So you have to make your telescope very, very cold. And that's done with the sunshade. The sunshade is the size of a tennis court. It's huge. And then to fit it in a rocket, it's all rolled up, and then the telescope folds up. So you can have a look at the pictures later, but this is showing it starting out folded up, and then how it deploys as it gets into space. Once we've launched it, this process takes about 3 months, and after that, we'll be starting to think about taking some observations with Webb. So because it's so big, and because it's so cold, it is literally going to be able to look at the universe in whole new ways. We've never had a cold telescope this big in space before. And so what's exciting about that is it opens up the opportunity of making discoveries. Yes, there's lots of things that we say now, okay, I know this and this and this, and then because I know all of these things, for example, about how galaxies evolve, so we think that galaxies start out as small clumps of stars, and then over time those clumps of stars gradually stick together, they collide, and they make the big beautiful galaxies that we see today. But there's a whole host of things in that jigsaw along the way of how it all fits together that we don't know about, and so Webb will be studying galaxy evolution. What we're going to talk about today is the other thing that Webb will be uniquely suited to do, is studying the chemistry of what happens at the detailed level of what is dust made of, what is planets made of, how does it all interact with the stars. And that's really exciting science, because we've never had good infrared spectrographs in space. They're quite difficult to build, and you really need a big telescope to get enough light that when you then make it into spectra, you can still see faint things. So Webb will have really unique capabilities. And one of the things we have to do now is figure out exactly what we're going to do with it. So like I said earlier, I have a team of about 70 scientists working with me, and we're looking at everything from dust to how the early universe formed, in sub-teams looking at the different areas of science. Libby actually works with me in Edinburgh, and she's one of our dust experts. So I think you're going to be privileged to be working with her on this project. But what she needs to do is find the right things to look at. And that's a problem that we have, because the way science with something like Webb is done is a general purpose observatory. So we have to apply, we have to write a case that says, this is the science I want to do, this is why it's going to answer some good questions about the universe, and then other scientists will look at that and review it and decide whether we'll get the time or not. So that means that the preparation time that we're doing now is a really important period before the launch as we're getting ready. We also don't get to keep the data. So for us as scientists, the data is all made public eventually, actually very quickly. So again, we need to be prepared, because if I've spent my time building this instrument and thinking about the science it's going to do, I want to be the first person to publish the science papers with it. Because, well, I've put all this work in for 20 years, but I'll only be the first person to publish the science papers with it if we're really prepared. So I think that, you know, this project is about getting prepared for a part of the science that the MIRI instrument will do. So MIRI is actually the coldest instrument on the Webb telescope. That means it can look at the longest wavelengths. It is very good at looking at dust. It's also very good at looking through dust. And so a very big part of our science that we want to do with mid-infrared instrument is all around understanding the chemistry of the things in the universe around us, measuring their spectra. It will be the first, what we call integral field spectrograph in space, working at these wavelengths. And that again opens up that when we actually come to take the spectra, we'll probably find things that we didn't predict. I mean, I'm sure we'll find some things that we can already predict, but I think we'll find lots of things that we wouldn't predict. And that's kind of, for me, that's what makes astronomy interesting. It's why I've spent 20 years building an instrument. It's also an exciting time for me, because I've spent a long time working with engineers, because I'm not an engineer, so a lot of my team was originally engineers, people who knew how to build the instrument, how to put the optics together, how to make sure it would work properly. And now I'm going back to doing science, because we're ready for the science and we're through really a lot of the complicated testing. So what's happening, James Webb Telescope will launch in early 2021. So that means that we've got, it seems like a long time, but actually that's a very short period of time to prepare for the launch. So we're also, all of the scientists are getting practice with what the data will actually look like and thinking about what we want to do in the right kind of level of data. And then once it launches, we'll start getting real data back to actually use to study the universe in new ways. So you're kind of joining the project at a perfect time, really, because this is a telescope for a new generation of scientists, and perhaps some of you will be in that. That's all I was going to say. I'm really happy to answer questions about JWST, but I think you really need to hear from Libby about the science and the project. So with this, I'd like to introduce Olivia Jones.